Christy, Rob, Allison, and Ming, are you all ready to go?
Ready to
Yes.
go.
Yes, I'm ready.
Okay, fantastic.
Ready.
I'd like to thank everybody for showing up for our 8th Climate Sensitivity and Cloud Feedback Virtual Symposium. On behalf of my co-convener, Christy Procesescu, welcome. Just a few notes. This will have 3 AGU style talks from Rob, Allison, and Ming. If you have any questions, type them into the chat at any time. Or if you prefer to ask questions live, you can raise your hand. If you go to the bottom of the screen, there's a icon that on my computer looks like a face. You click on it, it gives you options to like clap your hands or raise a thumb. It also has raise your hand. And if you do that, we can unmute you and you can ask your question. Also, after the last talk, we frequently have general Q&A for a few minutes, 5 or 10 minutes. So stick around if there's things you want to ask the presenters you didn't get to earlier. And lastly, we're looking for a few people to join our steering committee. So just to give you a little background, we started this about a year ago. In fact, it's March 10th, which is just about the 1-year anniversary of the shutdown. Also the 1-year anniversary of me wearing pants that have belt loops on them. Not literally, but very close to true. And, you know, all this time, Christy and I have been kind of cranking along, doing this. But, you know, at this point, we're kind of see the light at the end of the tunnel, and it's reasonable for us to think about what we want to do in the future. Do we just want to shut this down? Do we want to keep it going? So we're looking for other people to join our steering committee. And Nick Letsko has already agreed to join. We're looking for 1 or 2 more people. So if you're interested and you think this is something you'd like to do, help determine where we go from here, we'd love to have you. And so with that, let me turn it over to my co-convener, Christy.
Hello, everyone. Thanks for joining. Our first speaker of the day is Robert Pincus. He is a research scientist at NOAA CIRES in Boulder, and he will talk to us today. He will talk to us today about benchmarking calculations of radiative forcing by greenhouse gases. Robert, take it away. 10 minutes in, I will yell 10 minutes.
Hi, thank you. It's CIRES, not series, as you know down here. So sorry, I couldn't resist that because Andy put the wrong series in the name. So I'm going to talk about radiative forcing by greenhouse gases, and in particular, some results that have come out of the radiative forcing MIP. I was inspired to volunteer. You know, often you say, oh, thank you for inviting me. But of course, everybody who gives a talk in here is volunteering. And I volunteered because Nick Letsko showed this plot in our last episode. And he showed it as a way of saying, well, there's, you know, you'll recall that he was talking about the different impacts of uncertainty in forcing and uncertainty in feedbacks on temperature change at different timescales. And he showed this figure from a paper by Brian Soden and Bill Collins and Dan Feldman, talking about what they were describing as uncertainty in the radiative forcing calculations in climate models. And so they're going back to 1993, work by Bob Sess, and showing that for a sample calculation here, the doubling of CO2 from pre-industrial concentrations, there's a wide diversity of results from GCMs. And so that's in the first and the last column. So of order a watt per meter squared on several watts per meter squared. So a lot. And so the results from the right-hand column here are from an analysis of CMIP5. And you might ask whether that has changed in CMIP6, and the answer is not particularly. So one of the first talks in this series, you may remember, was from Chris Smith from Leeds, who was talking about results from RF-MIP as related to CMIP6, and in particular, looking at the diversity of forcing by carbon dioxide So these are scaled to present day concentrations. He's inferred here the instantaneous radiative forcing, which is, as this audience knows real well, just the change in the top of atmosphere flux due to a change in composition or concentration in the case of carbon dioxide. And so there's no adjustment by, well, okay, so this is inferred from GCM calculations, and you'll see that it's, the mean value is 1.2, 1.3 watts per meter squared, and the spread is still several tenths, 3 or 4 tenths of a watt per meter squared. For physics, we understand remarkably well. And so the question would be, how does the spread come about? And does this really represent the uncertainty we have in the radiative forcing to which the planet has been subject? And I would say that the spread does not, in fact, represent true uncertainty. Now, Brian Soden and his collaborators attributed the spread in model results to what you could think of as model error or parameterization error. So it's this phrase, right? The spread in the model calculations doesn't represent any fundamental uncertainty, but just the failure to do the problem correctly. Or you could say maybe a different, say it differently, it represents different cost accuracy trade-offs where the accuracy has suffered tremendously. And that's supported by the middle panel, which actually doesn't come from GCM calculations at all, but from a long line of intercomparisons stretching into the past and into the future from this 2006 paper by Bill Collins, looking at offline calculations. It's not a GCM, it's just the parameterizations extracted and applied to the same sets of columns. And you see that there's still a lot of spread among the GCM parameterizations. So as part of the radiative forcing MIP, which is associated with CMIPS 6, we have an experiment called this thing, RAD-IRF, that is aimed at diagnosing the parameterization error. It's not just for doubled CO2, it's for a wide range of forcing agents. It's also to sensitivity to temperature and humidity perturbations, which we've seen in the past have caused errors. And so we could assess how much error there is, but the climate model estimates are actually vary for another reason. It's not just the errors in the parameterizations. It's because the background climate varies among the models, and in particular, the temperatures, the distributions of temperature. So when we think about forcing, the state of the atmosphere matters. And there's a few different ways that one could look at this. Here I'm showing a figure from He Wang from 5 years ago or so. So to make the point that some of the diversity in forcing is due to state dependence. And that arises because the impact of a change in concentration at the top of the atmosphere depends on the temperature and humidity in the column. And that varies by quite a lot. And so you can see here, this is from 5 years of reanalysis, and it's done with an accurate radiative transfer model, and asks what is the zonal mean forcing from doubled CO2. So you see the all sky line in the red. I don't know, can I draw with my laser pointer? Or have I lost the ability to do that?
You should be able to show your cursor. I don't know what, if you're using PowerPoint.
Maybe I won't. Maybe I won't bother. You can see the bright red line, and that's the all sky forcing. And so to some extent, one of the things that's happening here is that where there are clouds, you might be hiding a change in concentration lower in the atmosphere. But the state dependence is just almost as pronounced in the clear sky, which hopefully you can see is the dashed blue line, which also shows you in the zonal mean. So in this paper, Yi Wang developed an interesting heuristic model for this. There's some, to my mind, really terrific, more theoretical work Jacob Seeley and Nader Jivanji have done recently that explain why this comes about. But the point is that you can imagine if there's a state dependence of CO2, if the CO2 forcing depends on the state, then different models will have different backgrounds and they will be different. And this is indeed something that we are finding to be true. So this is work by Ryan Kramer, who's at NASA Goddard, which is in review, in which he's trying to disentangle various sources of model spread in forcing, the spread in the model forcing. And what he's done is to try to understand, again, this is the spread in the instantaneous radiative forcing. He's asked what that is as he diagnoses it with a kernel, and then he's applied a consistent radiative transfer models in the blue and the red to compute forcing from average average states in a variety of CMIP models, and he finds that the majority of the spread is due to this variation in the states, so in the temperature and humidity distributions. And it turns out this in the brown line, it turns out that the majority of that is related to variations in temperature. So that's hopeful, because it means that if we want to interpret the historical record, what we do is we compute the forcing for the world that we've observed. So that is for the distribution of temperatures and humidities in the real world. And that is relatively straightforward to do. We would take an accurate radiative transfer model, and we have to sample enough of the variation in temperature and humidity in the real world to be able to capture that state dependence. And in particular, what I'm interested in for this talk is the global mean. That state dependence is a lot easier to characterize for clear sky than for clouds, for reasons that I'm sure are obvious. I was going to say clear, but reasons that are obvious to people. And that's just that clouds are substantially more variable. There's work going back to the 1990s that suggests that doing this with just a few profiles, so sort of mid-latitudes and tropical profiles, for example, will get you percent-sized errors. And we revisited this question when we were composing RFMIP. We have provided, as part of that experiment, 100 columns that are chosen from 1 year of reanalysis data. And what they do, the intent of these columns was to sample error in the forcing calculation, parameterization error in the forcing calculation. And we're able to do that to within fractions or hundredths, a few hundredths of a watt per meter squared. So we've provided the 100 columns, the left-hand panel, which is the only relevant one for this talk, shows you the sampling error, not just in the global mean, but in a whole bunch of different calculations. So top of atmosphere, surface, troposphere, different latitude bands, and so on. And you can see that the sampling error, which we did by using an accurate radiative transfer calculation, doing the brute force calculation, and then asking how representative our samples were of that. We're down to a few hundredths of a watt per meter squared. So these are not random samples, I should be clear. These are optimized through simulated annealing for what that's worth. But what it means is that with 100 columns, we have a very, very small sampling error. That is to say that we have a small sampling error in the parameterization error, but it also turns out that we have very small error in the forcing itself. It's not true of the fluxes for reasons I won't go into, but there you have it. We have sampled the forcing error small, we have 100 columns that represent the global mean radiative forcing, global annual mean radiative forcing. And then we have, for this experiment, 17 variants that include composition changes, which is to say radiative forcing. So the reason that we wanted to do this with just 100 columns is we wanted to get reference models, reference radiative transfer models. So we have 6 contributions from various institutions. These are line-by-line models, so they have very high spectral resolution. They have very high angular resolution. And they have contributed results to this experiment. And so we can use these to ask ourselves, what is the radiative forcing in the present day? So the agreement among the models is, to my eye, pretty good. You have on the left the long wave forcing, and on the right the short wave forcing, and the 3 columns in each figure represent the top of atmosphere, the surface, and the difference between them. These are net fluxes. And so I highlight the absorption because this is the thing that'll be most closely related to hydrologic sensitivity. Thank you. The agreement among the models is quite good, and this has been true historically, and that's because essentially all line-by-line models do the same physics, and they rely on the same underlying spectroscopic data. So even if you go back to the early 1990s, you'll see agreement within a few percent. The true uncertainty is conditioned on what we know about the spectroscopy, what we know about the interaction of gases with radiation. You can see that that's visible actually even here. The British have used a different representation of the water vapor continuum, so weak water vapor absorption far from lines. They used the caviar continuum as opposed to MTCKD, and that is more absorbing, and that greater absorption masks a little tiny bit of the forcing that is evident in the shortwave. So I should just say it's more absorbing in the shortwave, and so it masks a certain amount of the forcing. Yeah. So there's a few caveats to say about this result as an estimate of present day radiative forcing by here of all greenhouse gases at the present day. One is that the forcing calculations are perturbations to present day conditions. Normally, when we talk about forcing, we say, what is the perturbation relative to pre-industrial? Present day conditions are warmer and wetter, and forcing has a state dependence, so there's of course a small bias in our forcing calculations relative to having done it for the present day, which of course we can't observe. There's a wrinkle on this, which is that the surface boundary is spectrally uniform, which we did because we were focusing on model error. There's some experience, and you could look to papers by Lazarus Oreopoulos that showing that more realistic surfaces would change the forcing slightly. The big problem, of course, for understanding the historical record is that we have not treated the clouds. And the issue there is one of sampling. The clouds are enormously variable, and the degree to which they will mask or emphasize certain forcings is, needs to be sampled. People use various approximations, particularly to try and understand spread, but that doesn't really leave us with an error budget that's well suited to understanding what the true benchmark radiative forcing would be. I don't see any reason why we couldn't just sample all the cloud variability. There would be some obvious challenges in characterizing the diurnal cycle and in placing the clouds in the right place vertically in the column if one was interested in surface forcing. But someone ambitious could certainly go ahead and do that. I want to try and sneak in here another part, a calculation that we did in this paper, which exposes some interesting physics. Of course, what you'd really like to understand if you want to understand the historical record is the effective radiative forcing rather than the instantaneous radiative forcing. So you'd like to account for adjustments. For most greenhouse gases in most GCMs, the bulk of the adjustment comes from changes to the stratospheric temperature. The first adjustment that people identified. So the stratosphere, as it becomes more opaque, changes its temperature in order to maintain equilibrium. You can estimate the impacts of stratospheric temperature adjustment using what's called fixed dynamical heating, which just assumes that the radiative heating rates are going to stay constant. The profile of radiative heating rates is going to stay constant. We did these calculations in the paper that I've been referencing. And most of them are small, but two of them are not small and interesting. One of them is that the stratospheric temperature adjustment for carbon dioxide is about 50 to 70% of the instantaneous radiative forcing, and that's for interesting spectral reasons, which you can see. And ozone is a freak because the perturbations are not uniform in the vertical, and also because when you add ozone in the stratosphere, you make it warmer, of course, from solar radiation. And so the adjustment in the long wave is actually a large chunk of it is due to absorption in the short wave. So I would just maybe highlight those things that you could look at in the paper. So to close, I would make a couple of comments. One is the sociological question that I do not understand the answer to, which is why is it that we have physics we understand perfectly well, and yet our parameterizations of radiation in the climate models remain at odds or remain erroneous? I don't know. I think there's an interesting sociology study there. Just to reiterate the point that spread among, we all understand this in this context, but spread in the models doesn't represent true uncertainty. And in the case of radiative forcing, some of the spread is due to model error, but some of it is due to the state dependence of instantaneous radiative forcing. So if we want to interpret the historical record, one of the things, I guess the state of things is that we have very well characterized instantaneous radiative forcing by greenhouse gases in the clear sky. Estimates of what that means in the all sky, and a clear path forward to understanding the all sky instantaneous radiative forcing. And I will stop there.
Great, thank you. We have time for one quick question. Maybe two. Okay, Caitlin Loftus asks, this may be obvious, but could you clarify what you meant by sampling error in earlier plots?
Yeah, just the idea there is that you'd like to calculate the global mean. And so you could do calculations all the way around the globe, but that's expensive, especially for a line by line. So we wanted to pick a set of conditions that represented the global mean, and the difference between the small set of conditions and the full set of conditions is the sampling error.
Okay, and one quick question from Daniel. Interesting talk, Robert. Just back on the clear sky topic, does the two-stream approximation usually used in GCM codes not matter much compared to fancy codes?
So normally in the clear sky atmosphere, that word two-stream means maybe two different things. In the shortwave, we normally would think about it as a way to treat the scattering, the up and down scattering. So you would divide the radiation into two streams. In the long wave, you can just ask yourself how many, because there is no scattering, you just have to do an angular integral. And I don't know the extent to which that well, I think it's clear that it is treatments in the underlying gas properties that cause more of an error than limited angular resolution. But we could look at that actually in RFMIP if you were curious.
Awesome. Thanks. Okay, our next speaker is Allison Wing. She is an assistant professor in Earth, Ocean, and Atmospheric Sciences at Florida State. And, well, the title is up there. She's going to talk to us about convective self-aggregation, clouds, and climate sensitivity. Take it away.
Great. Thank you so much, Christy. Thank you for having me here today. And I'm going to present some of the results from our RC-EMIP project. And so I need to add about 40 other authors to this talk. So thank you to all the RC-EMIP contributors, and especially thank you to my graduate student, Catherine Stauffer, as well as Tobias Becker. And most of the climate sensitivity related stuff I'm going to show today was led by Tobias Becker. So I'll motivate this by noting that convection in Earth's atmosphere is organized on a variety of different spatiotemporal scales, from mesoscale features like squall lines and mesoscale convective systems, to synoptiscale features like tropical cyclones and equatorial waves, and then even to the planetary scale for phenomena like Madden-Julian oscillation. And this organization of convection is not just a spatial organization that makes for appealing pictures, but it also matters for climate. And so the observed cloud regime that corresponds to organized deep convection is responsible for about half of all tropical rainfall, as well as a significant fraction of tropical cloudiness. In addition, much of the observed regional increases in tropical precipitation that have been seen are associated with an increase in the frequency of this type of organized convection. And so it does have an impact on the hydrological cycle. Additionally, more aggregated observed states are on average observed to be drier, have fewer high clouds, and have greater outgoing longer radiation and greater tropospheric radiative cooling. And so this organization of convection impacts the humidity distribution and radiative and energy budgets. And when it comes to monthly variations on the scale of the tropics, a recent paper showed that more aggregated conditions actually also have enhanced net cooling at the top of the atmosphere. So there is an impact on the top of atmosphere radiation budget. One of the tools that we can use to investigate questions about convective aggregation and climate and clouds and how they all interact together is radiative-convective equilibrium, which is a statistical equilibrium in which there's an approximate balance between the net radiative cooling of the atmosphere and convective heating. And this is really a time-honored idealization for understanding the tropical atmosphere and its sensitivity to relevant forcings. It remains the simplest possible way to phrase many questions about climate, including questions about the response of clouds to warming and self-aggregation, where self-aggregation is a particular type of convective organization that emerges in simulations of RCE in which the convection self-organizes despite homogeneous boundary conditions and forcing. Now, there's been a sort of really large renaissance of studies in recent years using the RCE framework, but these studies have differed in many ways in terms of their setup. And so to really better interpret them, we need a common baseline for comparison. And so that motivated us to organize an RCE intercomparison project, RCE-MIP, where we're actually able to assess the robustness of the simulated RCE state. One of the other advantages of RCE is that it's a framework that's accessible by many different types of models. And so RCE-MIP includes participation from 30 models, including GCMs and single column models with parameterized convection, cloud resolving models, LES, and global cloud resolving models with explicit convection. And so it's pretty unique in its ability to kind of bring together so many different types of models. In all cases, the RCE is simulated by doing an aquaplanet simulation with totally uniform insolation and uniform sea surface temperature, no rotation, and where motion is just initialized from random noise. And we have two sets of domain configurations that we do. The first is a small domain, which is a 100 kilometer square for our cloud resolving models and LES, or a single column or small Earth for GCMs. And in these simulations, we have three at 3 different temperatures. An example for the icon model is shown on the right. Typically, we see that the convection is randomly distributed and unaggregated across the domain. We then have a set of large domain simulations, again at the same 3 temperatures, which is the global domain for the global models, and a 6,000 by 400 kilometer rectangle for the cloud resolving models, and examples of the different configurations are shown on the bottom right. And so we can then use this distribution of models in this RC configuration to address questions about clouds aggregation and climate sensitivity. So turning first to clouds, we find that across the majority of models, our anvil clouds rise in response to SST warming at a rate of about 0.3 kilometers per Kelvin. We find that the anvil cloud temperature increases slightly of 0.4 degrees per degree SST of warming, and that's roughly consistent with what you would expect from the proportionally higher anvil temperature hypothesis. And we also find that the coverage of anvil clouds decreases with warming in about 70% of the models, as shown here. In all cases, what's being plotted here is the values of these different anvil cloud properties at the 295, 300, and 305 Kelvin simulation, where for the cloud fraction, to see the slopes better, we've done it as an anomaly from the value at 300 Kelvin. And so one of the things we wanted to do was assess the validity of hypotheses to explain this behavior. And so in particular, one question was, does the arguments that have been made recently about radiatively-driven divergence, do they explain the decrease in anvil cloud fraction? And so according to the stability iris hypothesis of Bonidal in 2016, increased upper level stability in a warming climate as the anvil clouds are rising would require less clear sky subsidence per radiative cooling amount, thus resulting in less radiatively-driven divergence and less anvil spread. And so we can assess that in our simulations by comparing the anvil cloud fraction to the peak in the radiatively-driven divergence. And in our large domain simulations shown on the right, we do see strong evidence for a relationship between these two quantities. So the small dots here, those are the simulations at 295 Kelvin, and then the large dots are the simulations at 305 Kelvin, where here the values are given as fractions of the values at 300. And so basically, if we see simulations that are going from this top right quadrant towards the bottom left quadrant, then that says that both the anvil cloud fraction and radiatively-driven divergence are decreasing together with warming in those simulations. And so that's true for most of our large domain simulations. But when we look at the small domain simulations on the left, we see much weaker evidence. Most models do have a decrease in the radiatively-driven divergence with warming, but don't necessarily have the corresponding decrease in anvil cloud fraction. And we're still working on trying to explain the differences in the behavior between the small and large domain simulations. Turning now to the aggregation, here we can have a kind of overview of what the characteristics of convection look like in these simulations. These are the large domain simulations with the cloud resolving models on the left and the global models on the right, including to scale the global cloud resolving models, which used a smaller Earth radius, but then also blown up so you can actually see them. And so what's plotted here is outgoing long wave radiation. And we see that nearly all these simulations are aggregated, meaning the convection is sort of isolated in these different clumps with drier, clear air in between. There's huge diversity in the patterns of this organization, both in terms of scale and the structure. And if you played a movie, there's differences in the variability as well. But it's really sort of dynamic and fascinating. But it's nice to see that, you know, this phenomena does occur across a much larger range of models than had previously been used to investigate it. So getting into kind of more quantitative analysis of this, one of the things that the models do agree on, despite the diversity in how they distribute the convection, is that they agree that the existence of aggregation affects the mean state. And so we can compare pairs of large and small simulations for each model with and without aggregation to see what the effect of the aggregation is on the model mean state. And we find that with aggregation, there's fewer high clouds. And so this is showing profiles of cloud fraction, taking the difference between the large aggregated and small disaggregated simulations. So we have a decrease in high cloud fraction. We also find that the aggregated simulations are drier, both in terms of looking at profiles of relative humidity, as well as column integrated metrics like precipitable water. As we go from small to large simulations, we see a robust decrease in the precipitable water. We also find in terms of the temperature distribution that the aggregated state is warmer, and this then also caused our tropospheric average lapse rate to be more stable. And these changes have implications for the hydrological cycle and energy budget. And so the precipitation rate, the mean precipitation rate, is larger in the aggregated simulations. And this is consistent with the fact that there's greater net atmospheric radiative cooling in the aggregated simulations. And in terms of the top of the atmosphere energy budget, we find that there's more cooling to space in the large simulations through these clearer, drier, larger regions that are opened up when the convection is aggregated. In order to quantify the degree of aggregation a bit more, we use three different metrics. The first is subsidence fraction, which is the fractional area of the domain covered by large-scale subsidence, which is related to this transition to kind of narrower areas of convective convection, and then the larger areas of subsidence.
10 minutes.
Okay. We also use IORG, which is a clustering metric in which we identify convective entities based on a threshold value of outgoing long-wave radiation, compute the nearest neighbor distance for each convective entity, and then compare that distribution to what one would expect from a random distribution shown on the right. And so basically for both subsidence fraction and IORG, if it's greater than 0.5, then that means the convection is aggregated. And then the larger the number means the more aggregated or clustered that it is. We finally also consider the spatial variance of column relative humidity, which reflects the clear signature of self-aggregation in broadening the moisture distribution. So we compute all of these metrics for all of our different large domain simulations, and we get this picture here. So the red circles show subsidence fraction on the left axis. The blue squares show IORG on the right axis, and the green triangles show the column relative humidity variance on the right axis. Here we've put the cloud resolving models on the left half and the GCMs on the right half. And then the box and whiskers plots show the median and range of each quantity. And I think the big takeaway is these points are sort of all over the place. There's a wide spread across the models in the degree of aggregation. This is for the simulation at 300 Kelvin. We do see, though, that the metrics do tend to be correlated with each other. If we're considering across all models, subsidence and fraction and IORG are weakly correlated with a correlation coefficient of 0.46. But if we consider, say, just the cloud resolving models, then all three of the metrics are very strongly correlated. And so this is really good because it means even though there's a lot of variability across the metrics and across the models, a model that one metric says is highly aggregated would also be classified as highly aggregated in the other metrics as well. And so that's sort of reassuring in terms of the representativeness of the metrics. We can then also assess how aggregation changes with warming by plotting the rate of change of these different metrics with temperature. And so that's now what's shown here. It's D metric dt. And basically, if we look at all these points, we see that about half of them are above the 0 line and about half are below it. And so there's really no consensus about how aggregation changes with warming. Half the simulations have an increase, half have a decrease. It doesn't really matter which metric you look like. They all have a widespread that's centered around 0. One thing that we do notice, though, is that the right half of the plot here does tend to be a bit more likely to be above 0. And so the GCMs have a bit more of an increase in aggregation with warming than do the cloud resolving models. And that's going to be important in a moment when I talk about climate sensitivity. So moving now to climate sensitivity, we've shown that self-aggregation impacts the climate in these simulations. And so it's natural then to ask, does it impact the climate sensitivity or how the climate would respond to an external forcing? But first we need to know what is the climate sensitivity in the CMIPS simulations. So since these are simulations at fixed sea surface temperatures, we can assess climate sensitivity by calculating a CES type net climate feedback parameter by looking at the slope of the top of atmosphere radiative flux against temperature. And then that can be converted into an approximate value of climate sensitivity using a sort of reference value of radiative forcing. Now I know Robert just told us about how the radiative forcing is state dependent and model dependent, and here we're just saying let's just take a representative number just to kind of help give some context for these values of climate feedback parameter. So for our small domain simulations that have no aggregation, again, in our different configurations with the different resolutions, we see that climate feedback parameters would be consistent with a pretty high value of climate sensitivity. But we also note that the spread across the different models, the different colored lines here, tends to be greater than the spread across these different setups. That is to say, the LES models, which have 200-meter resolution, have a similar spread across the models than do their counterparts at coarser resolution, which is sort of interesting. If we then go to the large domain cloud resolving models where we have aggregation, we see that the spread in climate feedback parameter is much larger. We even have a few models that have a positive feedback parameter, which would indicate an unstable climate. And the spread is even larger yet when we go to our GCMs. If you notice also the black dot here is showing the mean across the models in that category. We see that the GCMs have on average a more negative feedback parameter, which would be a lower climate sensitivity compared to the models with explicit convection. Okay, so there's a wide spread in climate sensitivity, a wide spread in self-aggregation, also a wide spread in the changes in self-aggregation with warming. Do these things all explain each other? Well, it turns out that in about 70% of the CMIP models, though heavily weighted towards GCMs, the aggregated simulations have a more negative climate feedback or lower climate sensitivity than their unaggregated counterparts. And so aggregation perhaps lowers the climate sensitivity. However, it turns out that if we're trying to explain the intermodel spread, there's really no correlation across models between their sort of average amount of aggregation and their estimated climate sensitivity. However, there is a relationship between changes in the aggregation with warming and then the model's climate sensitivity. And so that's what's shown here, the climate feedback parameter on the y-axis, and then the change in IORG with temperature on the x-axis. The blue dots here are the cloud resolving models, the red are the GCMs, and we see that there's a robust correlation such that those models that have more of an increase in aggregation with warming are the ones that have more negative climate feedback parameters and lower climate sensitivity. And if you kind of delve into this a bit more, it turns out that it's mostly due to enhanced clear sky, outgoing lung of radiation due to mid-tropospheric drying in the simulations that become more aggregated with warming. The lines here show the mean across the different groups of models, and we note again that the GCMs are averaging more negative feedback parameter or lower climate sensitivity because those GCMs have on average a greater increase in aggregation with warming compared to the cloud resolving models, which really on average don't have a change in aggregation with warming. So to summarize, in the RC-EMIP ensemble, we've examined changes in clouds with warming and find the anvil clouds rise, slightly warm, and decrease in extent, at least in the large domain, roughly consistent with the stability iris hypothesis. When it comes to self-aggregation, nearly all models aggregate to some extent in the large domain, but there's a wide variability in the structure and degree, but there's agreement in terms of how they affect the mean state. But unfortunately, no consensus still on how aggregation changes with warming. For climate sensitivity, there's a large spread. One thing I didn't have time to show, but what is interesting is we're also working on making estimates of the cloud feedbacks in these simulations, and at least our initial estimate of the cloud feedback suggests that the intermodal spread is smaller in models with explicit convection. So that's maybe reassuring. But overall, we find that the climate sensitivity is lower in GCMs because they have more of an increase in self-aggregation with warming, though there's also a contribution from shallow clouds. And so if you combine together changes in shallow clouds and changes in aggregation with warming, then we can explain 70 to 80% of the intermodal spread in climate sensitivity. And so that's, again, the whole goal of these types of idealized experiments is that we hope we can actually keep things simple enough to figure out what's going on. And so with that, I'll end, but I'll just quickly leave you that we have a special collection about using RCE to understand climate, etc., across AGU journals. And so if you're doing work with RCE, please submit your papers to our special collection. It does not have to use the RC-EMIP data. It can be any sort of RCE experiment. Thank you very much.
Thank you, Allison. Thanks for this great talk. Maybe you can take one quick question from Steve Klein. Is there any relationship between the climate sensitivity of a GCM in RC framework and the climate sensitivity of a GCM in a realistic planet framework?
That's a great question. We haven't done a rigorous analysis of that yet, but we do have a paper in review focusing on the community atmosphere model suite of simulations. And CAM6 has a higher climate sensitivity in RC-EMIP compared to CAM5, just like the more comprehensive models do. But you have to be careful when comparing them because RCE climate sensitivity should really only be compared to like what you would get for like a tropical estimate of climate sensitivity. So it's a little bit of caveat there, but at least in that example for one model, it does seem to be consistent with the more comprehensive version.
Okay, in the interest of time, we have to move on, but we can continue discussion in the chat or at the end for a few minutes. So the last speaker of the day is Ming Cai from Florida State as well. And he's going to talk to us about a less cloudy picture of the intermodal spread in future global warming projections.
All right, can I share screen?
Yes, you should be able to.
Okay. All right, can you see my screen?
Yeah, it looks good. Just, yeah, looks good.
Thank you. Yeah, thank you, Andy and Andrew and Christy for inviting me here. You know, I'll volunteer, but thank you for the invitation. And this work is largely based on recent publication in Nature Communication. Here is my co-authors, Xiaoming Hu and Hanjie Fan, and Sergio Stahas, Patrick Taylor, and Song Yang. And here the climate projection uncertainty, the source of for that is largely can be loosely grouped into three groups. One is due to the internal climate variability. So this is physical. Another one is due to scenario uncertainty. That's mostly due to human, mean how we see our future ourselves in terms of carbon increase in the future. So it's less so much physical. The last one, which is the models due to model spread. So the question, this is a physical. The question is that why different model on the same amount, more or less the same amount of radiative forcing as rotational radiative forcing, they have different amount of warming. So there's a larger warming here. Okay. So I think the dominant the theory is the cloud feedback uncertainty. Cloud feedback is the major components contribute a climate projection uncertainty. So one thing here I just show here in the recent paper, Zenica and that shows that the clouds, the feedback parameters have a larger range. So different models have a larger range of the variability of the cloud feedback parameter strength. Okay, so other feedback strength is kind of tightly, very relatively narrow. Okay, so of course, if we use the PRP method, if we use this the feedback parameters, estimate the climate change. Okay, of course, if the parameter here is very large, variability large, you have a larger change of the even the fixed are the same. You have a larger uncertainty in the climate projection. So here the Bonner et al. 2018, they did similar work. Instead of using PRP, this energy balance TOA, they apply the moisture energy surface energy balance model. I did the same thing here. If they fix the feedback parameters, but keep the range, I mean uncertainty range, and in one of them, and they show that indeed the cloud, the projection made by the moisture energy balance model has a larger uncertainty. Okay, so in this kind of arguments, the model is by definition, because this value has larger range. Of course, this value will have a larger range, but that's not necessarily is the true cause of the model larger range. Okay, but anyhow, still is concerned why this feedback parameter has a larger range. So that's a separate questions. And recently, the people started to see whether the spread of the feedback parameters has to actually have correlation with the climate change projection spread. Okay, so again, Zenica et al. And 2017, they show the clouds. This is cloud feedback parameters. This is the warming projection. Okay, have a larger positive correlation. This seems to point to the true cause of the related to the cloud feedback parameters uncertainty to the climate change projection uncertainty. However, this correlation has kind of caveats, because when you use climate feedback parameters, you normalize by the warming amount. Okay, so this climate feedback parameters spread or prime is a departure of individual models climate feedback parameter with the MME value, multi-model SME value. So same thing with the temperature change uncertainty. So these two correlation here. So you can mathematically work on two terms, A and B. Okay, so A actually does not. So this have negative correlation built in here. Okay, this is the climate projection uncertainty. This is also climate projection uncertainty. This is the mean MME value, multi-model SME value of that feedback strength in terms of energy flux at the TOA. Okay, so if the feedback is very, very small, this term will be positive. This have built-in negative correlation. If this is negative, built-in the positive correlation. Okay, this is kind of reflect what we concern here, reflect the change of radiative forcing associated with that feedback, and here still they tangle together. Okay, so I demonstrate here. We demonstrate here. So this is we did the same calculation, use feedback parameters with the climate change. Okay, I mean projection uncertainty spread. So here this is correlation. Okay, this correlation here. Okay, again, cloud indeed the largest term, and the water vapor feedback is the negative. Okay, very, very small negative. But if you decompose it in two, because the ME value of cloud feedback is a larger positive, so as a result, you have a larger negative value here. Okay, so and then this positive, these two terms cancel out. Let's give you very, very small correlation in terms of feedback parameter for water vapor feedback. And for clouds, the mean ensemble mean cloud feedback strength is close to zero or small. Never so here and is positive but small, and here this value is small. Okay, so as a result, this two term does not get cancelled here. Okay, so you have a larger value here. So if you directly calculate the feedback strength in terms of energy flux and TOA, so with the climate temperature change spread here, now you see here the cloud no longer largest term, okay? Water vapor is the largest term, okay? And the albedo is also larger term, okay? So these three are equally important, but you can think water vapor is the largest contribution, okay? Planck feedback, of course, by definition is a negative correlation, okay? The nearly perfect one. So here in this study, we kind of follow the same idea, try to use correlation to identify the main source of climate change projection uncertainty. But we do a further step here. So this more like global mean projection spread, we call it spread, okay? It's uncertainty. So we see whether this global mean projection spread can be explained by few spatial pattern spread, okay? So basically different models have different warming pattern as a result, or different size, different amplitude of the same warming pattern, and can give rise to spread, okay? Then we link this spatial pattern of this to the climate feedback. So the rationale is that like what as a biofeedback, more likely concentrated in the polar region. If larger the pattern has larger spread in the polar region, more likely to the as a biofeedback. And if you do tropics, water vapor more strong in the tropics. So we use a pattern to further link to identify the source of the spread. So that's our rationale. And here, what we did here is we use the CMIPS model output, and the current climate is this 50 years mean of historical run, and we consider RCP 8.5 scenario. Okay, 50 years. Here, this is defined as the climate projection, and different model has different amount of projection, so we call that spread. Okay, and we have 25 models considered, and the warming projection. Warming pattern projection is so there's spatial pattern. We also identify the pattern projection. And the feedback, we use the partial temperature change associated with each process. So basically, we calculate the amount of temperature change due to each process. Then we see, of course, for same water vapor feedback, different model will have different partial temperature change. So that's what we call partial temperature spread. Okay, we consider here both pattern and global mean of this partial temperature change. So here, this show this scenario here. So this is a different model, have different warming amount here. The green curve, green line is the MME value, multi-modal ensemble mean. Here you can see this is the range of the spread, okay? And this is the MME mean spectral pattern here. Lunar averaging is green, solid black curve here. So this is variability. You can see this is different model have different patterns, okay? But particularly you see a larger pattern, larger uncertainty in the polar region. So this is our spread in the individual partial temperature change here. So lunar mean. So here and so if we add all together, it's more or less recover this part, okay? Except this is the error part, okay? Is except in the South Ocean and the polar region have other areas very, very small. So basically, our partial temperature change, if things can add up to the total spread here, okay? So we can think that at least in that part robust. And here we regress the global mean temperature projection spread with the pattern. Okay, so here basically there are only three patterns which can explain 92 or 93% of the global mean temperature uncertainty. The first pattern is more like so the model have larger global mean warming, so would have almost everywhere larger warming too, but with pronounced polar warming indication. But the model who has that does have small warming would have relatively less warming out the latitude with weaker the polar warming indication. The second mode is seesaw. Okay, some model predict southern hemisphere has more warming, some predict northern hemisphere has more warming, or vice versa. Okay, so it does not contribute global mean warming spread. And the another third mode, okay, explain the warming. So it's tropical warming more or less polar communication, or stronger polar communication, but with less warming in tropics. Okay, so here we do correlation of this global mean here. So this have a global mean here. So those model has less warming here, have negative pattern of this pattern. So this warming has a positive, stronger warming projection, has more a positive pattern. This, okay. So correlation is very good, 0.84, and this of course global mean 0, so this does not contribute to global mean spread. This has 0.28, has a global mean value here, so contribute to 0.53. If you add together, 99 correlation is 9.995. So basically, these two special patterns explain nearly 98% intermodal spread of global warming projection. So here now next we regress this pattern, okay, with the feedback with the individual partial temperature change here, okay. So that's we show here. So that's individual here. This mode 1 and 3, okay. So in terms of here, interesting here, definitely albedo, as we may expect for the mode 1, and the water vapor strong for mode 3, okay. So other also contribute this here. So if we do this, we add all 3 mode here, this global mean value here, okay. So we're ranking the model who has a weak, smaller amount of warming to largest amount of warming, which is the right curve, okay. And only from 3 mode, first 3 mode, okay, only for the first 3 mode. And the wild line here, a dashed line maybe is total. I forgot which one is which, okay. Our right curve is the first 3. So it basically first 3 explain the total warming spread. Now you can see here this nicely, show here this water vapor feedback, albedo feedback. So here the warming less, they have less water vapor feedback, okay? And the warming more have strong warming feedback, okay? So as also play a role here, this global mean value here, okay? And so this offset by the ocean heat, flux, okay? The surface flux, okay? So basically the surface flux trying to reduce the spread or cancellation of the spread due to water vapor here. But you do see clouds line up also nicely here, okay? Nice line up here. So for the 3 mode, for the remaining mode, okay, the remaining, and you see here, you don't see water vapor feedback and albedo feedback, or mostly, okay? You see here, mostly the other feedback we haven't talked about, include ocean heat storage term, and also cloud feedback too, okay? The cloud feedback have different combination, so they all cancel because this 3, all the term here at equal 0. This does not contribute to the global mean warming projection. So they all cancel, but different cancellation among the different model, okay? So that's here now we show this is a pattern variance in terms of individual partial temperature change and the total, okay? I think it's more meaningful look at percentage because so indeed the cloud has a larger spread, okay? Larger in pattern spread. Ocean heat storage actually have a larger spread. Flux has a larger spread, okay? And so in terms of percentage, okay, so of course, first 3 mode, this color, blue, first mode, and this kind of orange color, second mode, green is third mode, okay? So first mode, more than 92% of the variance explained, pattern. And the albedo, 70%, and the water vapor explained 80, close to 90, okay, 85. But so most of cloud variability does not contribute this pattern, okay? Does not contribute, only this gray part is so with the other mode, okay? Which has little contribution to global mean projection uncertainty. So that's the remaining part here. So now in terms of global mean, this is global mean projection spread, okay? So now you see here, this is nearly 100%, first 2 mode, okay? All the second mode disappear. Now the albedo feedback is 80%, and water vapor is like 95%, clouds 50%, okay? So that's still 50%, small amount, okay? And here we show at the TOA perspective. So basically the partial temperature change we calculate based on the surface energy budget. we do the same thing. We want to say, oh, that is due to the difference between TOA versus a surface. Actually, we got more or less the same pictures. Okay, so you see the plant vapor, of course, is largest one. Okay, and the albedo and the water vapor, a cloud is the third one. Okay, so this is lateral feedback. Okay, and again, you only in the global mean sense, cloud feedback percentage is increased, but compared to the albedo and the water vapor, still third one. Okay. So here, this is a summary. We identify two dominant warming projection spread pattern, whose global mean value is nearly 98%, 98.7% global mean warming spread. So first pattern corresponds that the model with the great global mean warming would have more warming everywhere, but with stronger polar warming allocation. Those with smaller global mean warming would have less warming everywhere with weaker polar warming allocation. The second pattern indicates some model with the great global mean warming has stronger warming in tropics. Okay, tropics warming that makes the model have stronger warming. Okay, and if the tropic warming is less, they have a smaller amount of warming. Okay, so basically the albedo feedback contributes to the first mode, water vapor feedback contributes to the second mode mostly. So that's the two factors explain these two spread are the key contributors to the intermodal spread of warming, global warming projection. Okay, so despite the large amplitude in cloud feedback, okay, but the little correlation with the intermodal spread of warming projection, different models experience different combination of cancellation between cloud feedback and other feedbacks. Okay, does not mean the cloud feedback do not exist. So the uncertainty is still very large, but they have cancellation with other process, and result does not directly contribute to the global mean warming projection spread. I think that's all I have. Thank you.
Thank you, Ming. That was a very interesting talk. Some very interesting results. Still trying to wrap my head around them. So it's 12:01. If people want to hang out for discussions, you're more than welcome to. But I do want to thank all the speakers and all the participants for joining us today. We'll announce the next set of speakers soon. We're still looking for volunteers. And yeah, I think that's it. Let's keep discussing if people want to discuss, unless Andy has something to add.
Just say we should probably take questions for Ming first before we head sort of the open discussion. If anyone has any specific questions for Ming, or if you have a general question for everybody or a comment.
I mean, I just have a question about the water feedback, because there are like several studies indicate the lapse rate feedback has a significant correlation, negative correlation with the water feedback. So add up the lapse rate feedback and the water rate feedback might indicate a smaller effect on the intermodal spread when we consider both of them. Will that affect your results?
I think so. Let me see. We did add it together. Yeah, does not change here. And so, yeah. So because the, I don't have this here. Yeah, we did calculate, we combine. So that's you already referred from TOA perspective. So our main presentation is based on surface perspective. For TOA or surface perspective, we don't have lateral feedback. We just we have air temperature feedback. Okay, so they are same thing here. So, and yeah, does not change the picture. Yeah.
Cool, thanks.
I don't have the results with me. So yeah. Oh, I do have. Let me see. Hold on.
I guess we could open it up to sort of just general comments, not just on Ming's talk, if people have them. Must be nice weather everywhere. People want to go outside.
Definitely nice here. It's like sunny and 73 degrees in Florida. Pretty perfect.
It's nice weather. I cannot turn on my blender, otherwise the sun, right? Full sun, yeah.
It's also nice weather in Ithaca, New York, which is shocking because that hasn't been the case in many months.
That first nice day is also always you really appreciate it after a long Ithaca winter.
Oh yeah.
And our students have 1 day of spring break at A&M. They have a 1 day spring break. So
We have no spring break at all.
I hope they
Is that
enjoy
because
it.
spring is 1 day long in Texas?
This year, spring break is because they don't want the students going out and getting sick and coming back. So they're doing everything they can to ruin spring break for them.
It makes sense, but I could really use a week off from teaching right now.
No doubt. No doubt. All right. Well, in the absence of any questions about it, let me thank all the speakers and the audience for their attention. And we will see y'all next month.
Yeah. Thank you.
Thank you.
Thanks, everyone.
See you.
Take care.